In this tutorial, we shall show you how to compute the scattering curve from a complex protein structure built from a single PDB subunit in a symmetry. More specifically, we shall compute the scattering curve from a microtubule. First, we will show you how to use scripted symmetry. We are building a subunit made of two geometric models, a sphere and a small cylinder. Both objects together are going to be our subunit. The cylinder is added to indicate the orientation of the composed subunit. The scripted symmetry is a Lua script that describes the symmetry of a microtubule, which is based on a three-start left-handed helical symmetry. We place our subunit made out of the sphere and cylinder in the scripted symmetry. The nesting result is a one-start helix. Both the location and the orientation of each instance is defined by the Lua script. We are now changing the parameters defined by the scripted symmetry, and the effect is direct. The parameters that we can change in the helix scripted symmetry include the radius, the pitch, the number of units per pitch, and more. Here we chose to work with the three-start helix model. Now, instead of the geometric composed object made of sphere and cylinder, we shall insert the atomic model of the tubulin dimer for the protein data bank, or PDB, by loading the PDB file of tubulin. After loading the PDB file, we are placing it in the helix symmetry. To get the correct microtubule structure, we can also rotate the atomic model subunit. When working with large structures, like this one, it is important to keep low level of details. To get the appropriate parameters for the computation of this type of large structure, we will estimate the size of the structure. We are using a computer that has a GPU card. We can therefore choose to use the GPU or the CPU of our computer. First, we choose to work with the CPU. We are entering the suggested parameters in the preference pane, and generate the scattering curve. The calculation is done on the CPU, and therefore is fairly slow. Look at the CPU usage, presented as a green square, at the bottom right side of the screen. Bright green represents working CPU, and you can see D+ is using all the available CPU cores of our computer. Look at the bottom left corner of the screen, where the progress percentage is shown. The first 30% of the computation time is spent on generating the 3D grid, which is essentially a lookup table in reciprocal space. This computation takes a while because it is a fairly large grid. On a GPU, the computation time is significantly shorter. Once the computation is over, the computation time is printed in the console of D+, and as you can see, the grid computation took some time, and orientation averaging was rather short. We shall now repeat the computation using the hybrid method. In the hybrid method, we compute a grid only for the subunit, and then this grid is used as a lookup table to compute all the translations and orientations of all the repeats of our subunit. We start by estimating the size of a single tubulin dimer using an enveloping cylinder, and enter the parameters into our Suggest Parameters tool. We are now seeing that for the tubulin dimer we only need a grid of size 50, instead of the previous grid of 180. We are placing the dimer back into the helical symmetry, and making sure that the checkbox Use Grid from here is only selected for the object we want to use the grid for, in our case the tubulin dimer. Again we click Generate, and wait. As you can see, the first 30% went by very quickly, as the grid is much smaller than in the earlier computation. Orientation averaging, however, is taking longer in this case. Altogether, the computation is done much quicker than the previous one. Now we will change the settings to use the GPU card of our computer. If your computer has a GPU card, you should use it and save a lot of computation time. We are going back to the full grid computation parameters, and change the integration method to Vegas Monte Carlo. Vegas Monte Carlo is an adaptive algorithm available when using a GPU and should be used for structures with one dimension different than the other dimensions. As you can see, the calculation was much faster. The grid computation time was accelerated by a factor of 40, and in some cases the acceleration factor can be even larger. When using a GPU card, we can still choose the hybrid method, and uncheck Use Grid from here checkbox of the symmetry. We keep the checkbox checked for the PDB subunit. We put a smaller grid size and click Generate. The computation is done, and it took a similar time. Using the hybrid method, we can create much larger structures. Here we have a microtubule with 48 3-start left-handed helical pitches. We are using GPU and the hybrid method, and click Generate. Look at the bottom right corner of the screen, where the CPU usage is shown. When the GPU is used, only one CPU core is used. Altogether, the computation took about 100 seconds, and you can see the layer line of the 3-start left-handed helical structure is much sharper and more intense in the longer microtubule model.